Okay, it's a great pleasure for me to introduce today's speaker, who is a colleague, a friend, and a very well-known astronomer, Leah Athanassoula. Leah studied physics at the University of Athens, then went to the University of Thessaloniki, where she did her PhD with the well-known professor George Kontopoulos. And 4 years later did a thèse d'état, which is equivalent to the German Habilitation, and worked as a postdoctoral fellow in Democritus at the beginning, then the European Southern Observatory, then the Observatory of Besançon, where she also obtained a permanent position, but decided to move later on to the Observatory of Marseille and the Laboratoire d'Astrophysique de Marseille. And now she's an emeritus professor of Aix-Marseille University. Leah received several awards. She got an award from the Ministry of Education of France for her publication record and the huge number of PhD students that she had. She obtained the Photinos Prize from the Academy of Athens for outstanding astronomical achievements. She obtained the highest prize in the Division of Dynamical Astronomy of the American Astronomical Society, the Dirk Brouwer Award, and this was awarded for lifetime work on numerical dynamics in these galaxies. Last year, she was elected Antepistellon member of the Academy of Athens, and also the same year, last year, was named Legacy Fellow of the American Astronomical Society. She has a huge number of publications and an H-index of 69. Her research was well-funded, both with money and computer time and computer equipment. And today, she will tell us, I see the title is slightly different than what we announced. We announced formation and evolution of structures in disk galaxies, but this is about the same, shorter disk galaxies and their structures. Leah, thank you for accepting to give us the colloquium today.
Thanks, Nick. This is a very nice introduction. Thank you. Good afternoon, everybody. So if you think, I'm going to talk about disk galaxies and the structures you see. If you think I'm going too fast, please let me know. And also, if you think that you want more information or less information, please let me know. I can adjust accordingly. Oh. Well, I can't. This is a mess. We did try.
Yeah, we did try and it worked before.
But that's always the thing. It works when the try. And afterwards it doesn't. Wait.
There it is.
There it is. It's a little bit tricky, but it's possible. Okay, so Hubble did a classification of galaxies, and he divided them in two big categories, one being ellipticals and the other one disky galaxies. So the ellipticals, the stellar component is in the form of something like a spheroidal or an ellipsoidal shape. Whereas the galaxies which have disks, they have most of their stellar mass in a thin disk component. Now he subdivided that again into two components. One, I don't know, can you see my cursor?
Yes, yes.
Good. So some of them have spirals which go all the way to the center, and another part has spirals which don't go to the center, but meet another structure which is elongated and is called a bar. And so this is again two different parts which Hubble classified. And let me show you some examples. Now, one of my favorite barred galaxies, this is a barred galaxy, as you can see it. One of my favorite barred galaxies is this one. It's NGC 1300, the one you just saw. And you can see that is a beauty. It's really fascinating. You see here, this is the bar. And there is a central part which is somewhat different. Remember that, because we're going to discuss it a lot. It's as if, you know, there's a bar here and a somewhat different thing here. And then there are spirals. And the spirals, you see little blue dots, and these little blue dots are simply young stars. Then notice also that there's two pieces like this, one nearly straight here, and another one even more straight here. And those are called dust lanes because they're lanes and because that they're constituted of dust, and therefore they shield the starlight, which is of anything that is behind them. And so they have this interesting form here. We'll see that later. So what we would like to see in these things is, why do we have such structures? Why do we have bars? Why do we have spirals? How do they form? How do they evolve? And why? And how do they? I mean, why is their form this way and not any other way? So this is, of course, I'm not going to say all that, but all the subjects I will have will be taken from there. And okay, again from this galaxy. Remember here, this is from the Hubble telescope. This is the spiral, and the spiral stops relatively here and relatively here. And so if you make a deeper exposure, what happens is that it doesn't stop here, but you can see it goes all the way here. And same thing here, it doesn't stop here. It goes all the way down here. And the other thing is that if you look at it like this, you have the impression that there is no mass here. All the mass is here, here, and here. But that is wrong. This is where the light is, and it's different to call about the light than the mass. The mass of the stars may be quite different. So for example, the star that has the most light does not necessarily have the most mass. And the stars, this part here is not empty. It's actually a disk. Now, this is very difficult to see, but please note my cursor. The disk goes like this. Here is probably the best position to look at it. And here you would have thought that the disk is a small perturbation. No, the disk is everything, and the perturbations are the bar and the spirals. This disk has most of the mass and not most of the light. So now we said we'd want to understand how those bars were formed and how everything went and why they are this shape and whatever. Now for that we need a tool, and the most useful tool one can think of is in simulations, because they can go very far in all their interpretation. And actually the ones we're going to talk about here is n-body simulations. When they started, it was the early 70s. It's a long time ago. And so at that time, computers weren't much. So you had to simplify things quite a lot, so that the most simple simulations were in the early 70s. They included gravity, of course, because that is the main force. And then as their name says, there were n bodies. That is, you take n point masses, n particles, n bodies, whatever you want to call it, and you put them as you think the object which you want to start with should be. So you just place them and give them a velocity. And then, of course, the more particles you have, the larger the number of n, the better approximation you're going to do, the better results you're going to get. But it means also a lot of computer power. And at the time, the only computer, well, there were two computers actually, which were very big, but the biggest and most important one was the NASA computer, which allowed for 100,000 particles. Now that's unheard of, was unheard of at the time, which is fantastic. So how do we get on? We start, as I said, with some particles, which have, oh, maybe I have it here. Yes, here we are. This is 2D. Think of it X and Y. If you looked at it vertically, it would be razor thin. And we put on this disk the particles according to a law which we think that they would obey normally in the real galaxies. So, for example, you put them like axisymmetrically to start with, and we know that the disks are exponential, so you put them exponential. And then once you have all those particles in place, you can start calculating the forces between two particles. So you have the two particles and you have the forces that this one acts on this one and this one acts on this one. Now there's another one here. And so this one has a force on this one and this one on this one and so on and so forth. Lots and lots and lots of this. And if you want to know what happens to this particle, you have to calculate all the forces of all the other particles on this one and sum them up. Now, of course, the world is three-dimensional, but at the time, the only thing they could do was two-dimensional. And of course, we know now that galaxies have a halo, and we want to, in the simulations, add the halo. Now that means taking some of our precious 100,000 particles and put them in the halo. So we don't want to do that. And what they did at the time was to add a halo to the equations of motion by adding a potential. So this is a rigid halo which cannot move. And we don't care how much force there is on this particle, which is the halo particle, but you care only how much force there is on the disk particles. And the halo, therefore, is rigid, whereas the disk is self-consistent. And then once you've done that, you say, okay, now I know the position of this particle, I know the velocity of this particle, and I know the forces on this particle. Well, then it's trivial. I will calculate the motion for a small displacement. So you allow that. And you allow that for all the particles. You calculate the forces for all the particles, and you do the total forces and therefore the motions. Of course, now everything has changed position, not very much, but everything has changed positions. The particles move during its forces, and you have to redo it again, because once you have new positions, you have new forces, new positions, new forces, and so on and so forth. So this is the simplest possible thing you can do. But what was nice was there was an enormous progress in computer technology in the last few years. And also there's enormous progress in the software which calculates the forces. You don't do two particles at a time now. Now you take a lot of particles and do on this one all the particles together. And that goes much faster. And the numbers now you can get because of these two advances is several tens or several hundreds of millions, and we're talking in billions, which is quite nice. We can now be three-dimensional. And now we can put all components represented by particles. There's no rigid components, or we try not to have any rigid components. And on top of it, the physics, the astrophysics of galaxies has advanced quite a bit. And we can do even better than before by adding, for example, gas. So there is gas, of course, it's got only a few % of the total mass, but it doesn't matter. As I will show later, the fact that the gas is there changes enormously things, much more than the 10% of you would have thought of for the beginning. We also add AGNs, supernovae, star formation, feedback, cooling. There's a lot of physics now. And even now, lately, we have added chemistry to those codes. So we do chemodynamics. There's a world of difference from here to here. You can go much further and do much more. But there was a lot of good stuff done in the old simple way. And here, for example, is some work by Frank Hall in 1971. Frank Hall was one of the few people to have access to this NASA computer, supercomputers. And well, what he did was he had 2D, that is the whole thing, and he wanted to study the bar instability. Since that is a disk instability, you want to, you use only, he used all his particles only in a disk, because he wanted to do also many simulations to understand certain things, as we will see. And so this is his initial conditions, and that's how it evolved. And look at this. It is not terribly different from this. With this relatively small number of particles, relatively easy, simple way, we managed to show that there's bars form and they drive the spirals. That's a nice big step, and that was done by Hall back in 71. Now he thought, okay, I did it once, now I'll do it more, I'll see how things go. So he did that, and he found that there were things like this all the time. Whatever he did, these things came up. There was always a bar. So after being very happy that we get bars, we started being terribly unhappy, because not everything, if you remember, if you remember here, not everything has bars. There are beautiful spirals without any bars at all. So why do the simulations show us that there is always bars? So now another simulation came up, which is perhaps the most famous simulation in astronomy. And that was done by Oestreicher and Peebles from Princeton, two very good names. Actually, Peebles has relatively lately had a Nobel Prize. This was back in '73. And they got together and they did simulations. And of course they didn't unfortunately have NASA behind them. So what they used is a small number, 150 to at the maximum 500 particles. So this was very simple simulations, but these people were very clever people. So they saw that there must be a reason for which the bar would not come. So what could that be? Well, in order to stop something from becoming non-axisymmetric, you have to make sure that the total force is not very far from axisymmetric, which means that you want another force, because the disk itself would create the bar. What does it mean you want another one? Well, that means a halo. So Oestreicher and Peebles put a halo on top of their simulation, and lo and behold, they cured the bar instability using a halo potential. So if this is sufficiently massive, if the halo was sufficiently massive, then they cured the bar instability. So this is fantastic. There was an incredible thrust on dark matter just with these simulations. Of course, people came about and said, look, you're talking about 150 particles, ha, 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 do you expect me to believe you? And therefore you and all your dark matter problems, that's not too good. Well, Hall came in '76, who remember had access to the NASA computers, and he did several runs, actually 5 of them. And he put here we have 80% of the mass in the disk. And in this simulation, we have 50% of the mass in the disk. And we have 3 times. And we notice that when it's 50%, when we notice first that 80%, you create a bar like before. But here with 50%, you don't. So they said, fine, this is it. People have had no more the excuse of, I don't believe it because of the 150 particles. And so the whole story of the halo and of the dark matter got an enormous push, an enormous step forward from this kind of stuff. Now we'll look at something which was done roughly at the same time. That was done in 1972 by two people who had no computer, or no computer worth talking about. And that was Donald Lynden Bell and Agris Kalnice. And they knew how to do analytics. So what they did was to look at a case with only a disk, no halo. Why no halo? Well, because this one happened in 73. They published in 72. The calculations were done in 1970. So they couldn't guess that there was a halo. So they calculated just the disk and looked, the approach they had is very much like the Landau damping, for those of you that did plasma physics. And they found that the bar forms under certain conditions. And what's more important, when the bar forms, of course, the positions of the particles, I mean, initially the particles were in circular motions, but when the bar forms, the particles will go differently. And so when the velocities change, the positions of the particles change, the velocities of the particle change, therefore the angular momentum change. This is the most important part. The angular momentum of each particle changes. So they looked at which particles gained angular momentum and which particles lost angular momentum, and they found that in a disk, the bar region, all particles there, lost angular momentum and gave it to the particles in the outer disk, which gained angular momentum. And they noticed that it was not all particles, as I just said, it's only those that are in near resonance. Now, what's near resonance will come in a minute, but now remember that. And then later on, about the 80s, when people realized that the halos could exist, there were Tremaine and Weinberg who did some similar things, but instead of looking, again, the angular momentum was taken from here, but they didn't use a disk in their calculations. They also were analytic, and they went directly to the halo. So here you have an outer disk, and here you have a halo. And then finally, people put them together. And so you have emission from angular momentum from the inner region and absorption from both the outer disk and the halo. Okay, well, why do I care about all this? First, let me tell you about the frequencies and what the frequencies here are. Now, suppose you have a particle that turns around in a circular motion around the center of the galaxy. Center of the galaxy is my finger. And they turn around. Now, the time it takes to turn is the period. And therefore, you have a frequency. Now, also, they don't make also only circular motions. They make more or less circular motions. So this one, for example, it's not a circular motion. The circular motion is the dashed line. The non-circular motion is this line. And therefore, we will have a second frequency, which is the radial motion. So here you're out, in, out, in. And so that way, we now have two frequencies, the angular frequency and the radial frequency, which for some reason people call the epicyclic frequency. Now, we have resonances if those two frequencies are commensurable. So for example, here you could have this kind of thing. So this would be the circular motion, and you might have an elongated orbit, much more actually than what I have it plotted here. And then you have, this is the time necessary for closing one circle. And now you go in, out, in, out. So you got twice in and out for once around. That's a resonance, a 2-to-1 resonance, which was worked by, a person called Lindblad worked on it. That's why it's called the inner Lindblad resonance. So we would now want to, we have now an idea and we want to see how all this goes. And the best way is to use, as I said, n-body simulations. So this is what is plotted here is the ratio of those frequencies. So here we have half, so a factor of 2. This is corrotation because there is omega equals omega of the pattern of the bar. And this is another resonance here. And there will be other resonances. For example, there's this is 2 to 3 resonance, I think. So what I do here is to take the particles and calculate for each particle the 2 frequencies, and then make a histogram, because this is only a histogram, the angular momentum exchanged, so lost or gained, as a function of the ratio of those frequencies. Now, you see several things. First of all, that this is the bar, this is the elongated, this is this kind of orbits, the elongated orbits, which if you put a lot of them one next to the other, would be the bar. And you'd see that the angular momentum was lost. Delta J is negative. So the first of the things that the Lynden-Bell and Kalnice predicted, that is that this part would lose angular momentum, now is shown to be true with a pretty high resolution simulation. Now, other places which were further out in the disk gain angular momentum. So we come and show that the inner disk you emit and in the outer disk you absorb. So the simulations proved these things correct. But there was a point here. Look at this. All this is the angular momentum that was emitted here. And all this was this little bit here is the angular momentum that is absorbed from the disk. But this thing has, the angular momentum cannot be created or lost. There has to be this, as much as you lose here, somebody else has to gain. So corrotation is obviously not enough because this is a small thing and this is a very big thing. And so this is the outer parts, this is the inner parts. So the inner parts want to emit much more angular momentum than the outer parts can possibly absorb. So what's going on? Well, just look at the next picture, which is the halo, the spheroid. And there you see that everywhere you absorb, that is, the angular momentum is gained at every position of the halo, not only the outer parts as we saw in the disk, but everywhere. And that there's plenty of it. So this is equal to this plus the integral of this. So we were happy because we actually managed to explain and find all the things that the analytical stuff had predicted was shown to be correct by n-body simulations. Yes, and there was another piece there was another prediction that as the bar loses angular momentum, again from the predictions are from Lynden-Bell and Kalnice, there you are, mainly, a bit from other people, but mainly those are the ones that get the benefit. So as the bar loses angular momentum, it should grow stronger. So one can look at the n-bodies, and this is the relative change of angular momentum, and this is the bar. And you see there is every simulation I could run has one point here. So it is true that the more angular momentum, the higher the angular momentum that you exchange, the stronger the bar. And it is a pretty good correlation, particularly if you think that each simulation is separate, independent. Right, so we can go a step further. And this is one of my favorite pieces. Look at only these, forget about these for the moment being. This is the face-on view of the disk. And what I did in this simulation, this is two simulations, the red and the green simulation. What I did was to take identical disks, that is, the disks were the same particles at the same position with the same velocities at t equals 0. It's identical. I use the same file. And then there is one difference. I make the halo here to be live, that is to be able to receive angular momentum. And in this simulation, I made the halo rigid, so it's just a potential. So they cannot receive angular momentum. And then I let the simulation run. This is the final result. This galaxy has practically no bar. It's a very small oval. This galaxy has a thundering big bar. So the halo can receive angular momentum, and the more angular momentum the halo can receive, the stronger the bar. Here, you cannot receive angular momentum, so it can only go as far as this little bit allows it. So we have the same simulation, but the only thing I do in this case, I stop the angular momentum exchange. Now, notice one thing. The halo, I mean, Oostrijkers and Peebles in 73, in that famous paper, they said, add on halo on top and the bar is gone. Here, I will tell you, add a big halo. If it is live, the bar grows and grows and grows, and you get the bigger possible. So practically, I'm saying just the opposite of what Oostrijker and Peebles said, except that, of course, I have this proviso that this has to be live and this has to be rigid. If they had a more or less rigid, then you would find exactly what Oostrijkers and Peebles found. It is a very strong result, and it is a result which, you know, at the beginning when I saw that, I said, oh, I've got it all wrong. It's absolutely wrong. It can't be. Oostrijkers and Peebles said that, so I can't possibly be wrong. So I reran the simulation. I redid some things. I redid other simulations of the same kind. I really did everything. Then I decided that I had to publish it. I did publish it. And people, well, I mean, you know, if you compare a young postdoc and somebody the order of Oostrijker and Peebles, you don't think twice. You say, well, these people were right and this one is wrong. So I had the hell of a time to persuade people that I was not wrong. But that the difference is simply that what Lindenbell and Kalnies called the transfer of angular momentum and how this can possibly help the whole thing. So what Oostrijker and Peebles said was correct only if the halos were rigid. That is, the halos could not take angular momentum, but the halos are not rigid in the real world. That's the main point. So, I mean, I was the happiest person when I would talk to either people or seminars or whatever, and people would be very polite and smile, and that would be it. And then at one point, somebody said, but that is obvious. And that was the beginning. People believed it. In order to be able to, well, maybe we should skip this one. It's not too much. Yes, and this thing also. So this is practically what I showed here, is what the halo can do, what the bar can do, how the bar grows, and why it is there. Now, you must have noticed that I did a big, except for this very last simulation here, all the rest were 2D. This is 3D, but okay, it's the only one. So we haven't said anything about the third dimension, the Z dimension. So the galaxies, if you look at them, the galaxies we saw in the beginning were more or less seen face on. Now we want to see something edge on. This is a galaxy which is edge on. This is a big bulge. But this is our own Milky Way, actually. This is the disk. And this is a boxy kind of thing. And this is Hickson 87A, another galaxy seen edge on, which has an X shape. So how does this thing come? Why do these boxes come? Why do these X's form? Well, again, orbits can come very, very handy. Orbits are simple. Everybody understands them. And therefore, it's something one should use as a tool to start with. If you simply say that the bar is something like that, and this is different orbits, and altogether they form the bar. Then I have plotted this way, and what I did also is plot the stable orbits in black and the vertically unstable orbit in red. This is vertically stable. This is vertically unstable. That means that if you start with this particle here, it will stay on the plane. If you start on the plane, it will stay on the plane. This one is unstable. If you start on the plane, it will pop up and do something else. And what will happen is this one, now instead of looking at face on, turn like this to a small angle. And then this thing will be, oh, I don't have any way to show it, but think of an elastic band. And this thing is this unstable orbit. It will not stay on the plane and will go like this. And if I look at it totally edge on, that is like that, here, this is all these orbits which stayed there because they're stable. And this is this orbit, which it's unstable, therefore they go in this shape. But if you look at this shape or this shape, you see something which is a little bit like this and a little bit like this, particularly if you don't have one orbit as I have here, but if you integrate over a number of orbits. For example, these things. This one is, as I said, our Milky Way. And this is this box I want to explain. Well, take a bar. Here's the bar. My arm is a bar. But instead of looking at it like this, I will look at it like this. That I will look along, the line of sight is along the major axis of the bar. Then what I see is this. So this box is this box. And it's not only like that, but if you take like this and like this, then it also makes a box. So we have something like this, which is about the 27 degrees, which are believed to be the bar in our galaxy. So yes, the shape of this thing is the shape of a bar. And now let me look at this one, where this one is, I see the galaxy, the bar now like this, and this is the simulation, and this is the galaxy. And the shape looks quite considerably similar. You see this X structure, which is also here an X structure. So there is a Z component to the bar. And that component can tell us a lot about, because it forms in certain cases, not always, because this instability that I have looked here is more valid, is stronger in some cases than in others. So there's a lot of stuff to be milked out from those kind of things. Now, let me look again in this geometry, this one here. So I have it here. And now I take my simulation, and what I'm going to do is to throw away all particles from the simulation, which are the halo or the disk. The whole disk is gone. What I see here is just the bar. Now remember this part, the outer parts of the bar in my very schematic thing, these parts were stable, vertically stable, so would stay on the plane. So here the bar is thin. Same thing here, of course, because it's the other side. In the inner part, it's unstable. So you make either this or an X, but you make, in this case, you make a box, or a peanut could be. So this is the kind of geometry one could see. And if you don't go like this, but you go like this, then this thing is what you would see, as which we do see actually in our galaxy. There was the observations of Ness et al., which showed that this is the kind of stuff you could show. Here you have the other way around. So this is the face-on. So I see my galaxy from the top above. I'm looked down on my galaxy. This is edge-on. So again, the galaxy here, but I'm looking along the minor axis here. And this is too intermediate to see exactly the angle. You please look at the squares. This is the squares because I've put the grid on the plane z equals 0. Here the grid is just a line because it's just on the z equals 0. And here you can see in projection how these squares would go. And you can see that this is the kind of stuff that one would expect. I will, if there is time in the end, I could show you a movie about it. So this much from the disk. So we've said two things so far. We said, first of all, how the halo works and what does it do to the bar? How does it help it? How does it go? We also showed that the vertical part of the bar can be important. We explained how that forms, how that evolves, and so on and so forth. And the next thing is, remember I said that we were lucky to live in a time when you could allow to put lots of physics in your simulations. And now I will going to try and put gas in the disk. But before I put gas in the disk, I'll do something very simple. I'll put gas in the disk, but I will assume that the distribution of matter in the halo is rigid. So I just want to see the response of the gas to that. And this is a set of 5 simulations. This is the disk, so I look at it from above. It is planar, just to make my life easy. And you will notice that this here is the outline of the bar, so this is more like an oval, and here this is like a bar. And this thing, and this is the result, so that I put a density of gas, and this is the result. So the bar, remember, is here. And black here is, the blacker you go, the darker you go, the less mass there is. The whiter you go, the more mass there would be, more dense, higher density. Which means there are some big gaps on the two sides. They are smaller if the bar is not very strong, that is if the bar is an oval. They're intermediate, and here they're the biggest. So look at also another thing. There is 2 lines. There's first of all a lot of gas in the center, lots and lots of gas, which is very important, this gas, because since it's shoved down here and gone into here, it gives the first part of feeding the monster. That is, if we have a black hole in the center and we want to feed it with gas, then this will have to go down here, and then into here. So this is the first step towards feeding the monster. And then there is these parts, which are quite thin, but very strong, because you can see that even though they're thin, there's a lot of white here. That is a lot of density, a very high density, very high mass. And remember, and this is the shapes that we found, because this thing, the shape of this thing is not straight, it's curved. And the shape here is straight with coming down here, and this thing is simply a straight line. And this is the observations. This is, we see that this looking at galaxies and thus drawing these dust lanes, we have things which are curved, straight, and then like this inside, or simply straight. And you must remember this galaxy, right? Here I had the dust lanes. Here I had the dust lanes. They come on either side of here. So what do I see? I see this. I see a lot of gas, a lot of stuff here. And I see this one, there's dust here, which absorbs the light. The gas is the dust and the gas have the same dynamics actually. And therefore I see this kind of stuff. So even simple response simulations can give you sometimes a lot of information. And this is the same thing, but not response. That is, I have a lot of, I put in stars, gas, and halo, all of them live. And this is the simulations. I did 15 simulations. There is different gas percentages and different different halo shapes. So this is a spherical halo, and this is an elongated one. And you notice that the more gas there is, the less the bar is strong. And the more triaxial the halo, the less the bar is strong. And also this is the gas, and you see that at the strongest cases, we find exactly what we found in the previous simulations, which were simple, no self-consistency. But we reproduce them pretty well in this case. How am I going for time, Nick? Am I through? Nick? Hello?
Okay, yes, I was muted. Yes.
Shall I stop here, or do you want to know more?
Yeah, you can talk for another 5 or 10 minutes maximum.
Okay. So what I would like to say then is, how does the disks form? Remember we said that here there are disks before we talk, and then we talked about the structure in the disk, but we didn't say how the disks were formed. So the disks can form in, well, let me go here. Yes. Now we know one thing is that the galaxies can merge also. We know that there's a lot of mergings going around, particularly at higher Z, when the galaxies are simpler in shape and have a lot of gas in them. The higher back you go in Z, in redshift, the more gas you find. And then those galaxies merge and we see what happens. Now, the first person to talk about this, the persons plural, was Toomre and Toomre. And they said, well, spirals and spirals will when falling into each other, they will make an elliptical. Now, this is wrong, as we will see, but it is fantastic because a little bit like the Oestrich and Peebles things. It's wrong, but it's fantastic. That is, for the first time, by throwing two galaxies at each other, we don't make garbage, we make another galaxy. So that's what they said. They said, throw a spiral onto a spiral, and what you will get is an elliptical. Now, again, although Toomre is a pretty well-known astronomer, he had the hell of a time to make it established. Apparently, I wasn't there, but I remember I read that de Vaucouleurs said, if two cars ram into each other, you don't get a new model car, you get a wreck. And this stuck. So after a while, and Toomre gave some simulations which were rather simplified. So people said again, that is because they're simplified. And the other reason is that the ellipticals they got were not fantastic ellipticals. That is, neither the profiles were very good out to the quarters, nor the shapes were actually what one would want for the ellipticals. So that was still, that was in the 70s. I forgot to put the date. But the other thing that we noted is that around the beginning, after, let's say, 2010, 2012, 15, a new component for galaxies came along. And that is the circumgalactic medium. There is gas, which is hot gas in the form of a halo, which is around the galaxy. We know that now. And so together with some other people, what we did was to say, okay, so far the results are not terribly good, what one gets when we do the mergings, but maybe because we stopped the circumgalactic medium from running. And yes, lo and behold, if this is the difference, this is a galaxy, this one first is a galaxy which makes something which seen edge on is like this, seen face on is like this. It's not a disk, it's not a good disk galaxy, it's not an elliptical, it's not a good elliptical. But if you, this is without any gas, without any circumgalactic medium. But now we put the circumgalactic medium, and the same thing, we just throw things at each other. Look at the difference, look at the difference. This one has a bar, a spiral, some external spirals. It's nice and thin, and this shape is what it should look like. So by actually trying to put a circumgalactic medium, we got into producing a disk. And I think I will stop here. Thank you.
Okay, thank you very much, Leah, for a very clear and pedagogical colloquium. I'm sure our students have appreciated this, because sometimes we get colloquia where our students and some professors like me are left out. So thank you very much.
I had a tutor. Somebody told me, be careful, you have to be understood by 3/4 in order for this.
That's right. This is what I consider a successful colloquium,
yes,
where people can go away and say, yes, today I understood how barred galaxies are made. So they will go home with one clear idea explained. Okay, so the floor is open for questions, and I will ask people to use their reactions and raise hands, or simply unmute themselves and ask the question. And until people, Vasilis has a question, so go ahead, Vasily.
Leah, thank you very much. This was a very, very enlightening talk. I was wondering whether you could elaborate a bit on the topic of feedback, right? Because star formation on massive disks in particular, not only transforms gas into stars, right? But injects energy.
Yes.
And that may have a substantial effect, for example, in the way a gaseous bar may form and the torques that may be exerted between a gaseous bar and a stellar bar. So how sensitive are the, I mean, people keep on putting more and more physics into, say, star formation, but often there is not, by definition, a very good control on the mechanism, right? So you
Correct.
get...
Correct.
Can you comment a bit on that, or?
Yeah, well, as you see, I have here included feedback. Now I have included two types of feedback: supernova feedback and AGN feedback. Now, I did it in two different ways. The first way was to take what other people told me was a reasonable way of modeling the feedback. For supernova, it's pretty easy. For AGN, it's more complex. So you have to assume that all sorts of things are correct. Then, and the results come reasonable out. You can also make them unreasonable. But the main points are that it can be reasonable. Now, when I was doing that, I thought of what one of the people I've learned most in astronomy from told me to do. That's Kevin Prendergast. I don't know whether you've ever heard of him, but he was a really incredibly sharp brain, and he really understood what he was talking about usually. And he had told me, if in order to understand and model something, you have to bring down 3 shelves of APJs and AJs and put all that stuff into your simulation, then change subject. And when I asked him, okay, and what am I supposed to be doing? He said, use simple parametric things. They will at least tell you what's allowed and what's not allowed. That was many years ago, and that was in the 90s. When I came to this point here, to your question, actually, I was wondering, well, I remembered those words, what he had told me. So what I did, except for the thing which everybody does, you know, to take some recipe for the AGN, some recipe for the supernova and try it. I simply took parametric descriptions. And although I cannot say why in any way this would be that way, I can say now clearly that the amount of energy ejected cannot be higher than that, should not be higher than that. The amount of energy ejected should not be lower than that, etc., etc., etc. And although I do not have a physical understanding of everything, I at least can say something and use some numbers. Now, the other thing about that is that you can get input from many other things which you wouldn't have believed would be input initially. So think of this AGN one, because that's the one that really hurts most. If you have the energy, this goes on the gas. So you think of it in computers wise, you have your black hole here, you have the gas here, and what happens is the energy pushes the gas away. What happens once the gas is pushed away is that the star formation will be less important in the center than before. And you can do that, and according to my little parameters and all that, I could say something about that. And the input now comes from the rotation curves of spirals, which were shown to have not a spike. I mean, the density distribution of was shown by observations. Albert was involved in some of those. The density distribution is not does not go into a very strong spike. It goes more like a low spike, a sort of 0.3 kind of thing, not -2. And if you do that, if you take that from the observations, then you can set a threshold, because the more you push things away, the more there is no star formation in the central parts, and therefore the -2 goes to -1, and the -1 goes to -0.5, and the -0.3. So that is the way to think about it. Try and get as much physics out of it as you wring as much physics as you can out of it. And then say, now I will consider that this is all I can do. And within these set of parameters, this is what will happen. The rest of it, I will have different funny things. That's all I can say at this moment. I don't know if it happened.
No, thank you. Thank you.
I don't know if
Kostas Stasis has a question. Costa,
Yes,
go ahead.
Yes, thank you. Thanks for this very, very eye-opening colloquium, at least for me. So let me ask a very naive question as a non-expert. What I got from your colloquium is that the presence of the bar is influenced a lot by the presence of a halo. And so if the halo is, so if the halo plays a very important role in the existence of the bar and how strong the bar is going to be, could you naively predict or estimate the baryon fraction, or how big the dark matter fraction of a galaxy is, just by how strong the bar is? And if not, why not?
Okay, this is not a naive question. It's a very difficult question, actually. Let me, you're absolutely right. The halo has a big effect on the bar. Now, you're asking me to turn it around. Knowing the bar, can I say something about the halo? So far, the first way, yes, I understand fully. Now you want the opposite. You want, given a bar, what can I say about the halo? Well, that would have been possible and would have been a lovely thing. And in fact, a lot has been written in the literature about it. There's a lot of ink spilled and nearly blood spilled also, I would say, for that thing, because people came up with just that, except that they rushed to Monthly Notice or ANA and published it. And now I would like you to look back at this thing. This is the bar, right? I have here 15 simulations. And this is the stellar component, and this is the younger stellar component. Here I have 0% gas, 20% gas, 50% gas, 75 and 100% gas in the simulation initially. Of course, afterwards with star formation, the fractions change, but here, and notice one thing, if I started with 0% gas, then I have this thundering big bar. I go down, and now I start the same simulation with 75% gas. Look at the size of the bar. So the halo is a main way of influencing the bar, but not the only way. Gas can do also the same thing, and some other ways, which, I mean, I didn't have time to go into. But here you see that in order for me to be able, it's like as if you are in a multi-parameter space, like you have parameter X and parameter Y, and then you have Z, and Z depends on X. That's fine, but it also depends on Y. So you cannot say, I know exactly what's going to happen with X, because if somebody told you first, yes, this is Y, then you go ahead and say, well, indeed, what is X? But you can't otherwise. So here, for example, the halo in all those 5 simulations was exactly the same. But if I had looked at this galaxy in the sky and had seen this big thundering thing, and had looked at this galaxy in the sky and had looked at this measly little thing here, I would have said this has an enormous halo and this has a lower halo. No, they have the same halo exactly. I mean, the simulations were run explicitly with the same halo. But here there was no gas, and here there was 75% gas. So it's a multi-parameter space, and you can't define one of the axes without knowing all the rest. And it's worse even than that, because the gas is not the only secondary parameter. Sorry, it's not the only parameter. There are other secondaries which grouping together can make it even worse for you. And as I said, then you have that to explain to people. And that, again, is not trivial to do.
Okay, I understand, but we can handle multi-parametric relations, right? I mean, the fundamental plane is a multi-parametric relation, and yet it's extremely important, right? So if you can identify 2 of the major parameters, and 2 of them are, I don't know, the halo mass and the gas, the amount, the gas content, And if two of those are observationally determined or determinable, right? Like the gas we can see, we can observe, right? And the strength of the bar we can see.
We can see the gas now, not gas at t equals 0. This simulation is gas now. And stars now, and this is gas now. And that's what we see actually in the real world. But we don't know what you started with.
I see. So it's the initial conditions. It's not the current. Okay, I see. But then, okay, if you zoom back to the early universe and the high redshift observations, which are now coming online, right? In the early in these proto-galaxies, you can still measure the gas. And you can still kind of, they are resolved now, right? And they will be even more. So you will be able to determine the presence of the bar and quantify it somehow. Could you then turn it around and say something about the dark matter of these galaxies? I mean, that would be of fundamental importance.
That would be very important, and I think that it should be tried. It's not trivial to work it because it's not sure that it's t equals 0, actually. It might be, and I think it is, the gas at the moment the bar is formed. See, the bar is not started with, you don't start with a bar. We start with something without a bar. And when you start forming it, how do I show it for you? Like this, I think. So you form the bar and get stronger, and then it stays more or less constant. And that means that you have to know at what time you have to look at. So you have to, and you can't look at those galaxies. You don't know how far off they are from there. You can find little bits in the center, but you don't know that they're young. It's very complex. It is worth trying, that's for sure, because statistically something can be said when we get those things. But that's all. And first, one would have to start it statistically on things like this. That is, suppose I had I mean, I have just 15 simulations here, but I can make more, of course, and other people can make more. And then it would be, we have to do that, take the simulation and put them into the observations, not the observations to the simulations. Take these simulations and assume that they're the real galaxies and say, okay, I'd make it like this one formed the bar at this time, this one at that time, this one at that time, and this is what I see. How does one manage to get one back all the way to the halo? That is that's the way. And in fact, well, yes, I am working on that.
I'm very happy to hear that. It's a very complicated project, but at least,
Yes.
I think it's worth attempting, especially now with the next generation of telescopes coming along, right?
Yes, hope I'll be there to see it.
Thank you.
Okay, there was another question. There was another hand up. If the person is still around, please go ahead and ask your question.
Yes, well,
Yes.
hello. Okay.
Yes.
Thank you. It is not so involved of a question, but I was wondering, how do we explain this boxy shape of the bar? I mean, the distinct angles that we saw.
This one?
Yes, in the real pictures also, we indeed saw it of our Milky Way. Yeah, because you said the planes are not. We cannot explain it with the planes.
Well,
yeah, maybe if you have not understood, Leah, I think that's it. Yes, you've said
Yes.
it, but say it again.
okay.
Yes.
Look, this one is the face-on. So I look at the galaxy from z equals 0, and I look down upon it. And it's ellipses, and they form a bar. So you mentally think that they can continue like this, and there's more here, and there's dense. There, I can put more in this region also, and so on and so forth. If these ellipses are vertically stable, then they cannot pop up from the plane. The plane is here. You start an orbit here. If it's vertically stable, it can't do that. On the other hand, if it is vertically unstable, it must do that. So this orbit here, the red orbit, is unstable. This is a toy model. Huh? This is unstable, so it will have to get out of the plane. It can't stay in the plane because it's unstable. It's a little bit like taking a pen and standing it like this. You can't. So it will fall. And where does it fall to? Well, it falls to a shape like this, which is actually, if I had an elastic band, I don't have, wait. It will be like this shape.
Yeah, so the distinct angles come from only the closer orbits that are affected.
Yes. These orbits are they're not everywhere, and further out they're not. So the bar itself is thin in the outer parts and thick in the outer parts, in the inner parts, because this part is unstable and this part is stable.
Yeah, it's clear. Thank you.
Okay, and I will ask the last question. Leah, out of curiosity, from observations of disk galaxies, not bar galaxies, disk galaxies, we know that the distribution of the stars is exponential in radius and exponential in z, where z is perpendicular to the galactic plane. Have we understood these exponentials from first principles, that is, with simulations?
With simulations, yes, but it's not understanding. It's actually, all we did was to say that, yes, there are here. This is a case with a big exponential. Here you are. But there also, we know that there are broken exponentials, which is this, and broken exponentials, which is like this. This is three simulation. No, sorry, this is NGCs.
These are real numbers.
Yes, well, I mean, I don't have them. I think no, I don't have the simulations, but they look very much the same. I mean, there's hardly any difference between the observations and the simulations. There's hardly any difference. So we know we're on the right track, but we don't understand why. Okay. Now, why? There is a possibility. There was a very interesting paper, if you want to look at it further, by Scott Tremaine and somebody else, which I forgot, unfortunately. And they looked at how this thing would evolve in certain ways. And there is quite a bit. It's not a trivial paper. It's a paper you have to take some time over. And they look at how entropy goes. Entropy is one of the things that could matter. And so they look at what different distributions and try and see how the exponential form helps with the entropy.
And similarly for the de Vaucouleurs profile, the R to the quarter law.
No, that's even worse. We don't know anything about it.
No.
I take it back. We do know something about it there. Something very good, actually. Don and Linda Bell wrote a paper, but that's a long time ago, where he showed that it is possible to explain that a little bit. Yes. Now, to be frank, I don't remember that paper very well, how it ran. Okay. But it's Lyndon Bell, just that's it. I mean, no co-authors. And he did look at the whole thing, yes. It's violent relaxation. What he did study was some stuff which was in violent relaxation. And he found that it is not necessarily R to the quarter, but it's not very far from R to the quarter.
Okay. Well, last chance for last question. Else, we will thank the speaker, and I am already clapping my hands. Thank you, Leah. Thank you very much.
Welcome. Glad you liked it.
Thank you very much, Leah. Thank you.
Glad you liked it.